All right, so we're going to start with question 5. Question 5, I've gone over this a few times in office hours. I was kind of joking about it because I think I drew it out about 3 different times just today alone. So when ammonium chloride dissolves in water, the solution becomes colder. The solution becomes colder because it's absorbing energy. It's absorbing energy from the water. It's absorbing energy from the surroundings. So when something goes into solution and it gets colder, it feels colder because heat, right, is going into that solution formation, right? So heat is on the way in, and that's what makes it feel colder. It's absorbing that heat from your hand, right? And that's why it feels cold to the touch, right? Same reason we put ice, right, in a drink. Melting that ice is endothermic. It absorbs the energy from your water, cools it down. So we know this solution formation is endothermic. So delta G equals delta H minus T delta S. So it's endothermic. That's a positive delta H. So ultimately, for this to be spontaneous, we need a negative delta G. So for an endothermic process, in order for that to be spontaneous, we need to have 2 things. We need to have a large temperature, right? We need to have a high enough temperature, and we need to have a large enough change in entropy, right? Positive change in entropy. So for question 5, right? Solution formation is endothermic. We get over that fact that it's endothermic because we have a large enough change in entropy. So that outweighs the fact that it's endothermic, right? Still confused on how this is an endothermic process, right? It's endothermic because it feels colder, right? It's colder to the touch. So it's absorbing energy, right? It's absorbing energy from the surroundings. And that's the definition of an endothermic process. It's absorbing energy from the surroundings. Exothermic would feel hot because exothermic is releasing energy to the surroundings, right? So when you touched an exothermic reaction or thought of an exothermic process, right? Like a combustion reaction, your fireplace, that's exothermic. That's releasing heat, that's giving off heat, right? Endothermic is absorbing, it's ending up at a higher energy because it's absorbing energy from the surroundings. In this case, the water are the surroundings, and that's why the water gets colder. That's why it would feel cold to the touch, because it's absorbing that energy. So yeah, question 5 would be choice D, right? It's an endothermic solution formation, right? That still happens spontaneously because of the increase in entropy. Question 6 was very similar, just figuring out which of those 2 we'd have to come together for that to be spontaneous. All right, question 7, given the following information, what is the melting point of phenol, right, in degrees Celsius? So 2 things here for question 7. And this equation might not be there in the exact same way on the bottom of the exam, but I'll write it up tomorrow if it's not on the paper, right? Anytime we want to find the equilibrium, so for a reaction, we can find that equilibrium temperature, or for a process, a phase change, right? That's temperature equals delta H divided by delta S. We want to make sure they're both in the same units. So either we're going to convert both to joules or we're going to convert both to kilojoules. I'm just going to convert entropy to kilojoules, so we've got the same units. So got 36.66 joules per Kelvin, right? We know there's 1,000 joules in 1 kilojoule, so we divide by 1,000.03666 kJ per Kelvin. So now I can find my temperature. Temperature equals my delta H is 11.514 kilojoules over my entropy, 0.03666 kJ per Kelvin. I divide those two, and temperature equals, let's see, 11.514 divided by 0.03666, and I get temperature of 314.07 Kelvin. One more trick here. They've made this a little bit trickier than they needed to be, right? They asked for temperature in degrees Celsius, and we found it in Kelvin. So let's see, degrees Celsius equals Kelvin minus 273.15. So degrees Celsius equals 314.07 minus 273.15. To get our melting point of phenol as, so minus 273.15, something like 40.9 degrees Celsius. Yeah, if you want to use 273, that's fine with me. The conversion is 273.15, but most of the time when we do the calculation, we just use 273 because that's pretty close. So yeah, question 7, anytime you're asked for a melting point or boiling point, that's an equilibrium position because you're at equilibrium between both of those phases. So we could use temperature equals delta H over delta S. We could also use this to find the flipping point of a reaction where it becomes switches from being spontaneous to non-spontaneous. All right, question 8. Oh, and this was multiple choice. So 40.93 degrees, right? The closest one, 41 degrees Celsius. It might already be there. I'll see. Question 8, right? Definitely going to have a question like question 8. Question 9, all of these summation calculations. So question 8, what is the delta H for this reaction? Please report your answer to 3 significant figures. Right, so delta H equals the sum of how many moles and the delta H's of my products minus the sum of how many moles and the delta H's of my reactants. All right, so I've got mercury 2 oxide breaking down into mercury and oxygen. So that delta H is going to be, got 2 moles of mercury, and that's at 61.38 kilojoules per mole, plus oxygen, which is 0, minus the sum of my reactants. I've got 2 moles of mercury 2 oxide at minus 90.79 kilojoules per mole. We're going to multiply through by our molar coefficients, and moles cancel out. And that's going to give us a delta H of 2 times 38. So 127.76 kilojoules minus a negative 181. 0.58 kilojoules. So we're going to add that across, and I get a delta H of like 300 and something. So plus 122.76. Yeah, I get a delta H of 304.3 kilojoules. It asked for the answer to 3 significant figures. So to 3 significant figures, right? Delta H equals 304 kilojoules for that reaction. we'll get to question 10, and then I'll stop the recording at question 10, and then I can answer that question as well. Sandra. All right, so yeah, we'll go back and do question 9 because question 9, right? I need the answer for question 9 to answer question 10. So we just found delta H was 304 kilojoules. So question 9, we'll find our change in entropy for this reaction. It's the same summation calculation, right? Entropy products minus the reactants. So, all right, I've got 2 moles of mercury, and now the entropy of my mercury is 174.9 joules mole Kelvin, plus oxygen is 205 joules mole Kelvin, minus, right, my 2 moles of mercury 2 oxide, and the entropy there is 70.27 joules mole Kelvin. So same thing, we're going to go through, multiply by our molar coefficients. Moles cancel out, moles cancel out. I'm going to add these two together, and then I'm going to subtract. So 174.9 times 2 plus 205 gives me 554.8 joules per Kelvin minus 140.54 joules per Kelvin. All right, I subtract and I get a delta S of 414.26 joules per Kelvin. Now we can jump into question 10 because I needed the answer from question 8 and the question 9 to answer question 10, right? We need both of those. One more thing before I get going. No one pointed it out, but we had to do this to do question 10 anyways, right? We want those units of energy to be the same. So we're going to convert from joules per Kelvin into kilojoules. So I know for every 1000 joules, I've got 1 kilojoule. So our entropy is 0.414. And yeah, they asked it for 3 significant figures. So yeah, our entropy is 0.414 kilojoules per Kelvin. Now we can answer question 10. All right, so entropy equals 0.414 kJ per Kelvin. So for question 10, it's a delta G calculation, free energy. So delta G equals delta H minus T delta S. We know it's not a summation calculation. We know it's not delta G equals the sum of the moles of delta G of my products minus the sum of how many moles and the delta G of my reactants, because I don't have delta G values for everything in the reaction. So therefore, it's just a Gibbs free energy calculation. So delta G equals, my delta H was 304 kilojoules. It's an endothermic reaction. I'm running it at 25 degrees Celsius, which is 298 Kelvin. And my entropy, I do have a positive change in entropy, 0.414 kJ per Kelvin. I multiply, Kelvin cancels out. That's going to leave me with kilojoules, and that's good because delta G should be in kilojoules. So 304 minus 298 times 0.414. And I get a delta G of about 180.6 kilojoules, so to 3 significant figures, right? Delta G equals about 181 kilojoules, right? That's positive. So this process is non-spontaneous. This reaction is non-spontaneous at this temperature, right? It's endothermic, but it does have a positive entropy. So that means at low temperature, this would be non-spontaneous. We see that here with a positive delta G, but at a high enough temperature, right, this reaction would become spontaneous. We could actually find that out, right? Temperature 304 divided by 0.414. All right, 304 divided by 0.414. Yeah, this reaction becomes spontaneous at 734 Kelvin, or, like 416 or 461 degrees Celsius is where that reaction would become spontaneous. All right, any questions on 10?